Testing, can you hear me? Testing, can you hear me? All right, so I'm going to be reading this book again. Last stream, I learned about indexing and about B trees and 2-3 trees, but the thing is, I feel like I should have saved this for the end because after I learn about general trees, graphs, and advanced data structures, I will read some of the chapters I skipped, for example, file processing and memory management, because these two chapters are more on the operating system side. So I feel like indexing, I should have saved it at the end and not last stream. Anyways, I'm going to study about general trees this time. Uh, Many organizations are hierarchical in nature, such as military and most businesses. Consider a company with a president and some number of vice presidents who report to the president. Okay, let's just get this. A tree is a finite set of one or more nodes such that there is one designated node R called the root of tree. If the set T minus R is not empty, these nodes are partitioned into more than n disjoint sets T0, T1, Tn minus 1, each of which is a tree whose root is R1, R2, and Rn. Here you have a big tree, the root R, but we can have uh, partitioned into disjoint sets. Oh, so we can break this part out and break this part out. And then P would be the root of this subtree. And then this over here would be the root of this subtree. And that's what they're saying. The subsets Ti from 0 to n are said to be the subtrees of T. These subtrees are ordered in that Ti is said to come before Tj. By convention, the subtrees are arranged from left to right with subtree 0, T0 called the leftmost child of R. A node's R degree is the number of children for that node. A forest is a collection of one or more trees. Each node in a tree has precisely one parent, except for the root, which has no parent. From this observation, it immediately follows that a tree with n nodes must have n minus 1 edges because each node, aside from the root, has one edge connecting that node to its parent. Before discussing general tree implementations, we should first make precise what operations such implementation must support. Any implementation must be able to initialize a tree. Given a tree, we need to access to the root of the tree. There must be some way to access the children of a node. In the case of the ADT for binary tree nodes, this was done by providing mumma functions that give explicit access to the left and right child pointers. Fortunately, because we do not know in advance how many children a given node will have in a general tree, you cannot give explicit functions to access each child. An alternative must be found that works for an unknown number of children. One choice would be to provide a function that takes as its parameter the index for the desired child. That combined with a function that returns the number of children for a given node would support the ability to access any node or process all children of a node. Fortunately, this view of access tends to bias the choice for node implementation in favor of an array-based approach, because these functions favor random access to a list of children. Practice and implementation based on a linked list is often preferred. An alternative is to provide access to the first child of a node and to provide access to the next sibling of a node. Here are the class declarations for generic trees and their nodes. Based on these two access functions, the children of a node can be traversed like a list. Trying to find the next sibling of the rightmost sibling would return null. The GT node value is leaf parent. Oh wait, so it's a doubly linked list? Parent leftmost child. Right, leftmost child. Right sibling. Uh Wait, is there no function for left sibling? Set value, set parent, insert first, insert next. What do they mean by this? Insert first child, they mean? Remove first, remove next. Public interface gentry. Clear root, new root. Clear root, new left child. There are traditional tree traversals for binary trees, pre-order, post-order, and in-order. For general trees, pre-order and post-order traversals are defined with meanings similar to their binary tree counterparts. Pre-order traversal for general tree first visits the root of the tree, then performs a pre-order traversal of each subtree from left to right. A post-order traversal of a general tree performs a post-order traversal of the root's subtrees from left to right, then visits the root. In-order traversal does not have a natural definition for general tree because there's no particular number of children for an internal node. An arbitrary definition such as the leftmost subtree in order, then the root, then visit the remaining subtrees in order can be invented. However, in-order traversals are generally not useful with general trees. It's pre-order and post-order, right? I will just actually I will just write it down over here. Pre-order and post-order. So this is a pre-order. Pre-order prints the root first. Post-order prints the root last. Okay. So root, then go to this subtree. Root, then go to this subtree. Root. Go back, go to this subtree root. Go back, go to this subtree root. Go back, and then B, and then F. So R is printed, right? A, E, curse, B, pre-order, F. No children, no more children. Perform a pre-order traverse. It is necessary to visit each of the children for a given node from left to right. This is accomplished by starting at the R's leftmost child. Call it T. From T, we can move to T's right sibling, and then to that node's right sibling, and so on. Pre-order. Where is the printed value? We do not process until all the children have been processed. It is necessary to visit each of the children for a given node from left to right. Pre-order means the root is printed first, right? Hold on, let's go back. Post order. Oh, this they talk about post order. So they start with the left, then right, and then root. Reach process. So C, then D, then E, then A. Yeah, B. In a general T, it's left, root, right, right. Left node, then the root, and then the right. But it's not defined over here. General trees are trees whose internal nodes have no fixed number of children. Compared to general trees, binary trees are relatively easy to implement because each internal node of a binary tree can just store two pointers to reach its potential children. In a general tree, we have to deal with the fact that a given node might not have no children or few children or many children. Even in a general tree, each node can have only one parent. If we didn't need to go from a node to its children, but instead only needed to go from a node to its parent, then implementing a node would be easy. A simple way to represent such a general tree would be to store for each node only a pointer to that node's pointer. We will call this parent pointer representation for general trees. E- Clearly, this implementation is not general purpose because it is inadequate for such important operations such as finding the leftmost child or right sibling for a node. Thus, it may seem to be a poor idea to implement a general tree in this way. However, the parent pointer implementation stores precisely the information required to answer the following useful question. Given two nodes, are they in the same tree? To answer this question, we need only follow the series of parent pointers from each node to its respective root. If both nodes reach the same root, then they must be in the same tree. If the roots are different, then the nodes are not in the same tree. The process of finding the ultimate root, given node, we call find. Parent pointer represents at most the parent pointer representation is most often used to maintain a collection of disjoint sets. Two disjoint sets share no members in common. A collection of disjoint sets partitions some objects such that every object is in exactly one of the disjoint sets. There are two basic operations that we wish to support. Determine if two objects are in the same set. Okay, and merge two sets together. Because two merged sets are united, the merging operation is called union. The whole process of determining if two objects are in the same set and merging the sets goes by the name union/find. To implement union find, we represent each disjoint set with a separate general tree. Two objects are in the same disjoint set if they are in the same tree. Every node of the tree has precisely one parent. Every node of the tree except for the root has precisely one parent. Thus, each node requires the same space to represent it. The collection of objects typically stored in an array, where each element of the array corresponds to one object and each element stores the object's value. The objects also correspond to nodes in various disjoint sets, so we also store the parent value with each object in the array. Those nodes that are the roots of their respective trees store the appropriate indicator. Note that this representation means that a single array is being used to implement a collection of trees. This makes it easy to merge trees together with union operations. Here is an implementation for a parent pointed trees and the union find process. General tree implementation for union find. The node array. Size. What is this? Oh, parent pointer tree. So we have an array of children. Each node is its own root to start. Merge two subtrees if they're different. Union int A int B. Root 1 find A, root 2 find B. Okay. And if the roots are not equal, array root 1 is equal to root 2. Find the roots. Find the root of the current tree. Current. Initially it's negative 1. Current is array dot current. So parent pointer tree int size. Array new int size. So they're initially all negative 1. Merge two subtrees if they are different. So I don't understand if they're initially all negative 1. When you use the find function, it's just going to return this value, right? Because all of them are negative 1. The parent pointer tree class has an array where each array position corresponds to one object in some collection. Each array element stores the array index for its parent. There are two main methods to implement. Method union merges two sets together, where each set corresponds to a tree. Method find is used to find the ultimate root of the for the for a node. Application using union find operation should store a set of n objects where each object is assigned a unique index in the range of 0 to n minus 1. The indices refer to the corresponding parent pointers in the array. Class parent pointer tree creates and initializes the union find array. The methods union and find take array indices as input. So wait, we have f over here. F is the root. This would be f would be negative 1, right? J would be negative 1. Okay, here is a tree. F is the root. 5. And then has the parent at 5. G has a parent at 5. I has a parent at 5. D has a parent at 5. Then E has a parent at 3. B has a parent at 0, which is A. C has it at 0. Consider the problem of assigning the members of a set to disjoint subsets called equivalence classes. Recall that an equivalence relation is reflexive, symmetric, and transitive. Thus, if objects A and B are equivalent and objects B and C are equivalent, then we must be able to recognize that objects A and C are also equivalent. In this representation, since A and B are equivalent, then they must be in the same tree. Likewise for B and C. We can reorganize that A and C are equivalent because they must also be in the same tree. There are many practical uses for disjoint sets and representing equivalences. For example, consider this graph of 10 nodes labeled A through J. A, B, C, H, B, C, H. But H connects with the, this is not the same tree. This is not this rearranged. Notice that for nodes A through I, there is some series of edges that connects any pair of these nodes. But node J is disconnected from the rest of the nodes. Such a graph might be used to represent connections such as wires between components on a circuit board or roads between cities. You can consider two nodes of the graph to be equivalent if there is a path between them. Thus, nodes A, H, and E would be considered as equivalent, but J is not equivalent to any other. A subset of equivalent edges in the graph is called a connected component. The goal is to quickly classify the objects into disjoint sets that correspond to the connected components. Another use for union find occurs in Kruskal's algorithm for computing the minimal cost spanning tree for a graph. The algorithm seeks to select the cheapest subset of edges that still connects all of the nodes in the graph. It does so by processing all edges of the graph from shortest to longest, only adding an edge to the connecting subset if it does not connect to nodes that already have some series of edges connecting them. The input to union find algorithm is typically a series of equivalence pairs. In the case of connected components example, the equivalence pair would simply be a set of edges in the graph. An equivalence pair might say that object C is equivalent to object A. Object C is equivalent to object A. If so, C and A are placed in the same subset. If a later equivalence relates A and B, then by implication C is also equivalent to B. Equivalence classes can be managed efficiently with the union find algorithm. Initially, each object is at the root of the tree. Equivalence pair is processed by checking to see if objects of the pair are in the same tree by calling find on each of them. The roots are the same, then no change need be made because objects are already in the same equivalence class. Otherwise, the two equivalence classes should be merged by the union method. Parent pointer representation places no limit on the number of nodes that can share a parent. To make equivalence processing as efficient as possible, the distance from each node to the root to its respective tree should be as small as possible. Thus, we would like to keep the height of the trees small when merging two equivalence classes together. Ideally, each tree would have all nodes pointing directly to the root. Achieving this goal all the time would require too much additional processing to be worth the effort, so we must settle for getting as close as possible. A low cost approach to reducing the height is to be smart about how trees are joined together. One simple technique called the weighted union rule joins the tree with fewer nodes to the tree with more nodes by making the smaller tree's root point to the root of the bigger tree. This will limit the total depth of the tree to O log n because the depth of the nodes only the smaller tree will now increase by 1. Depth of the deepest node in the combined tree can only be at most 1 deeper than the deepest node before the trees were combined. The total number of nodes in the combined tree is therefore at least twice the number in the smaller subtree. Thus, the depth of any node can be increased at most log n times when n equivalences are processed. Here is an implementation for the union method when using weighted union. Root 1 find A, root 1 find B. We take the weights. Okay. The following slideshow illustrates a series of union operations with weighted union. We now demonstrate a series of union operations. Processing pair AB, the root of A is A, size A is equal to 1. Since weights are the same, make the second root point to the first. Okay. Processing CH. So they combine C and H. F and G, weight is 1. Alright, F and I, weight. Root of F is F, size F is 2. Root of I, size I is 1. So the smaller one combines with the root of the bigger one. Root of D is D size 1. D and E combine. A and H combine. Hold on, what do they mean? Processing pair A and H. Root of A size A is 2. Root of H is C size C is 2. Okay. Since the weights are the same, make the second root point to the first. Then size of A is 4. E and G. Root of E is D and size D is 2. Root of G is F and size F is 3. Alright, makes size F 5. H and E. Root of H is A, size of A is 4. Root of E is F, size of F is 5. Combine them. And what about J? Nothing with J. The weighted union, wait, hold on, go back. Never mind. Weighted union rule helps us to minimize the depth of the tree, but we can do better than this. Path compression is a method that tends to create extremely shallow trees. Path compression takes place when finding the root for a given node X. Call this root R. Path compression resets the parent of every node on the path from X to R to point directly to R. This can be implemented by first finding R. A second pass is then made along the path from X to R, assigning the parent feed of each node encountered to R. Alternatively, a recursive algorithm can be implemented as follows. Let me see an example. You show how union nodes H and E, how to union nodes H and E with path compression. H and E, we find their parents. Change the parent of all nodes on the path from H to A, point to A. Change the parent of all nodes on the path from H to A to point to A. Okay. Change the parent of all nodes on the path from E to F to point to F. Union nodes HE make F the root as size F is greater. Okay. So all the subtrees just becomes children. Like all the deeper nodes just become the direct children. Path compression resets the parent of every node on path from X to R to point directly to R. Okay, so all the internal nodes of the subtree, they point to the root directly. To be more precise about what is meant, path compression keeps the cost of each find operation very close to constant. To be more precise about what is meant by very close to constant, the cost of path compression for n find operations on n nodes is approximately theta n log star n. The notation log star n means the number of time that log of n must be taken before n is less than or equal to 1. Example, this is 4 because log of this is 16. Log 16, 4, log 4, 2. Finally, log 2 is 1. Okay, thus log star n grows very slowly. So the cost of a series of n finds is very close to n. To be more precise about what is meant by, not this. Note that this does not mean that the tree resulting from the process of n equivalence pairs necessarily has depth theta log star n. One can devise a series of equivalence operations that yields theta log n left of the resulting tree. However, many of the equivalences in such a series will only look at the roots of the trees being merged, requiring little process time. The total amount of processing time required for n operations will be theta n log star n, yielding nearly constant time for each equivalence operation. This is an example of amortized analysis. The expression log star n is closely related to the inverse of Ackermann's function. Okay. You will be given a series of node pairs to union together. Each pair there is some node should become the immediate parent for some other node. Okay, the English is wrong. Union nodes G and A. So G goes to A. What? A goes to G? Oh, I see, I see. So the first one I'm clicking becomes the parent. C and D. C is the parent. What? D. I don't understand. Union nodes C and D. Click that should become a parent. Click on that should become the child you first click on. So C should become a parent. D should become a child. Things are reset to the beginning of the step so you can try again. This is correct. What do they mean? A and D. So A, B, H and G, H and E. So we have E and then H becomes a child. H and D. So A goes under E. F and I. F is the parent. A and C. A is the parent. F and C. A is the parent again. Finished. Okay, last time I think that was an error. Next, we consider a fundamentally different approach to implementing trees. The goal is to store a series of node values with a minimum information needed to reconstruct the tree structure. This approach is known as sequential tree representation. Uh, this approach, known as sequential tree representation, has the advantage of saving space because no pointers are stored. It has the disadvantage of accessing any node in the tree. Any node in the tree. It has the advantage that accessing any node in the tree requires sequentially processing all nodes that appear before it. In the node list that appear before it in the node list. In other words, node access must start at the beginning of the node list. Processing nodes sequentially in whatever order they are stored until the desired node is reached. Thus, one primary virtue of the other implementations discussed in this section is lost: efficient access to arbitrary nodes in the tree. Sequential tree implementations are ideal for achieving trees on disk for later use because they save space. The tree structure can be reconstructed as needed for later processing. Sequential tree implementations can be used to serialize a tree structure. Serialization is the process of storing an object, it's a series of bytes, typically so that the data structure can be transmitted between computers. This capability is important when using data structures in a distributed processing environment. Sequential tree implementation typically stores the node values as they would be enumerated by a pre-ordered traversal, along with sufficient information to describe the tree's shape. If the tree has a restricted form, for example, if it is a full binary tree, then the less information about structure typically needs to be stored. A general tree, because it has more flexible shape, tends to require the most additional shape information. There are many possible sequential tree implementation schemes. We will begin by describing methods appropriate to binary trees, then generalization to an implementation appropriate to a general tree structure. Because every node of a binary tree is either a leaf or has two, possibly empty children, they take advantage of this fact to implicitly represent the tree structure. The most straightforward sequential tree implementation lists every node value as it would be enumerated by a pre-ordered traversal. Fortunately, the node values alone do not provide enough information to recover the shape of the tree. In particular, as we read the series of node values, we do not know when a leaf node has been reached. However, you can treat all the non-empty nodes as internal nodes with two children. So it's okay. So A, B, C, empty D, E, F. No, wait. Empty D, empty, 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 and then we go to A's child. This is what the sequential representation in the area was generated by a simple pre-order traversal. Right. I mean, they said we cannot know if it's a leaf node. I think it is possible to know if it's a leaf node because the bottom layer would be 2 to the power of something, right? So if you know how many nodes there are, we can figure out how many, like the last k, how many of the last k nodes. We can figure out a number k such that the last k nodes would be the leaf nodes. So we can figure out. So 1, 2, 3, 4. Oh no, it's not arranged like that. It's in a pre-order traversal. It's not like it's not. Oh, I see. I see. No, no, empty, empty. Yeah, yeah. Alternative to illustrate the difficulty involved in using a sequential tree representation for processing, consider searching for the right child of the root node. We must first move sequentially through the node list of the left subtree. Only at this point do we reach the value of the root's right child. So remember when we learned about the storing an array in a heap representation? So we have R over here, and then this would be R. And then the first subchild would be here. Then the second child would be here. Let's put that over there. And then the two children of A would be here. Let's call it C, D. So C, D. And then the children of B would be this over here. So children of B is E, F, and then children of C in D. Children of C would be these two. Children of D would be these two. Children of E would be these two. Children of F would be over here, over here. So every time we fill up from the end, F, we are making a complete tree because it's filling from the leftmost side. So we can tell whether a let's say this array is full. We can tell if it's a leaf node. If actually we can't because the tree ends over here, right? It doesn't end over here. I was gonna say we can tell it's a leaf node by checking the last 2 to the power of n elements of the array. I child of D J K. Anyways, assume that each node value takes constant amount of space. Another example would be if the node value is a positive integer and null is indicated by the value 0. From the full binary tree theorem, we know that the size of the node list will be about twice the number of nodes. The overhead fraction is half. I don't know what's this. An example of what? Sequential representation is space efficient but not time efficient. What's the full binary theorem? Number of leaves in a non-empty full binary tree is one more than the number of internal nodes. We know that the size of the node list will be about twice the number of nodes. Extra space is required by the null pointers. You should be able to store the node list more compactly. However, any sequential implementation must recognize when a leaf node has been reached. That is, a leaf node indicates the end of subtree. One way to do this is to explicitly list with each node whether it is an internal node or a leaf. If a node X is an internal node, then we know that its two children immediately follow X in the node list. If X is a leaf node, then the next node in the list is a right child of some ancestor of X, or the right child of X. In particular, the next node will be the child of X's most recent ancestor that has not yet seen its right child. However, this assumes that each internal node does in fact have two children. In other words, that the tree is full. Each children must be indicated in the node list explicitly. Assume that internal nodes are marked with a prime apostrophe and the leaf nodes show no mark. Empty children of internal nodes are indicated by slash, but the empty children of leaf nodes are not represented at all. Note that the full binary tree stores no null values with this implementation, and so requires less overhead. The sequential representation in the array was generated by simple pre-order traversal. Now we will see how to reconstruct the original tree. Pre-order, and then empty child over here. Then D, right? But the thing is, how do we know beforehand how deep the tree is? Like, why not D as a child of this? Like, how do we know that C not is not a child of D? E, wait, how did we, uh, uh, how did we know G goes here and not here? So over here, A, B, slash D slash C, E, G slash. Yeah, I think if it encounters an empty node, then we go to the parent. So A, B slash, then go to the parent. D slash, then go to the parent. C, E, G slash, then go to the parent. So E, G slash and slash, then we go to the parent, and then we go back to E. But then the next child is slash over here. And then F, H, H, slash, so we go back up to I. Okay. So this I understand. This we mark it as an internal node, right? Explicitly list each node whether it is an internal node or a leaf node. So a node X is an internal node, then we know that its two children immediately follow X in the node list. So if this is an internal node, this is a leaf, this is internal. Storing in extra bits can be considered saving over storing in null values. The example above, each node was shown with a mark if it is internal and no leaf if it is a leaf. This requires that each node value has space to store the mark bit. This might be true if, for example, the node value was stored as a 4-byte integer, but the range of the values stored was small enough so that not all bits are used. An example would be if all nodes value must be positive, the high order signed bit integer value could be used as the mark bit. I see, I see. So if we are storing an 8-bit integer as the node's value, we can use 7 bits. So we have a smaller range, but the last bit could be used to indicate if it's internal or leaf. Another approach is to store a separate bit vector to represent the status of each node. In this case, each node of the tree corresponds to one bit in the bit vector. A value of 1 could indicate internal and 0 could indicate a leaf node. 1, 1, 0, 0, 1, 1, 0, 0. Internal node, leaf, leaf. Okay, I don't understand this. Storing generates by means of sequential implementation requires that more explicit structural information be included with the node list. Not only must the general tree implementation indicate whether a node is a leaf or internal, it must indicate how many children the node has. Alternatively, the implementation can indicate when a node's child list has come to an end. The next example dispenses with marks for internal or leaf nodes. Instead, it uses a special mark, close bracket, to indicate the end of a child list. So R children, A, C, and then end. And then what is this D over here? So R children, A's children. Okay, let me see what they do. All leaf nodes are followed by this symbol because they have no children. So R, A, C. and okay, so when we are adding a new, all right, now I understand. So we keep going. If we don't encounter this closed bracket, we keep going deeper and deeper and deeper. If we go encounter this closed bracket, we go one parent up. BF. Why do we need to do this? Can't we just end it at F? Okay, the next chapter is about graphs. So this is the end of the chapter. Using close bracket to signify the end of the structure, use sequential representation for this tree. A. So we keep mentioning the leftmost child, C, E, and then the close bracket. Then the no wait, yeah, and then the next child F. Go to the parent. So F, go to the parent, and then go to the parent again. Now we have D, go to the parent. But it should end with D. Parent. Why do they want it to end in the root? Okay, I get the point. Okay, the next chapter is about graphs. So I will end the stream here then. And yeah, I will see you guys next time. Bye.